Okay, so we just proved that all minimal polynomials are irreducible. So if I have some alpha, minimal polynomial of alpha over whatever field is irreducible. It's going to be a partial converse to that, and it just says that any irreducible monic polynomial is the minimal polynomial of something. So suppose you have a subfield of C, and you have an irreducible monic polynomial over it. Then there exists some alpha in C, which is algebraic over K, such that alpha has minimal polynomial M. I guess I didn't use the FT. All right, it's algebraic over K just because it has minimal polynomial M, so it satisfies this polynomial equation. All right, proof. Well, let alpha in C be any root of M. C is algebraically closed, which it says the fundamental theorem of algebra holds, which says that all polynomials of positive degree have a root in C. So we take one of them. This is given by the fundamental theorem of algebra. Then what do we know? We know that M of alpha is 0, and hence the minimal polynomial, M sub alpha, divides M. Because the minimal polynomial divides every polynomial that has alpha as a root. But both M alpha and M are irreducible and monic. So they're both polynomials that are irreducible, which means cannot be divided properly, and have leading coefficient 1. Well, that means they must be the same. All right. So all minimal polynomials are irreducible, and conversely, if you have an irreducible monic polynomial, it is the minimal polynomial of something. Let me point out one part of this proof here. This alpha was just any root of M. What this is saying is, kind of algebraically, all the roots of a irreducible polynomial are the same. So this motivates a definition, and we're going to define a word that you've used probably a lot of your life, but this is the proper definition here. So let alpha be algebraic over a subfield K of C with minimal polynomial M alpha. The zeros of M alpha are called conjugates of alpha. Conjugate in the sense that I just said, not in the group theory sense, but just conjugates. Okay, so as a quick example, we've dealt with these polynomials t squared minus 2, which is the minimal polynomial of the square root of 2. So this is irreducible, we showed that. So this means that root 2 and negative root 2 are conjugates. We also had t squared plus 1, and this was the minimal polynomial of the imaginary number I. So this means that I and negative I are conjugates. We've also looked at t cubed minus 2, which is the minimal polynomial of the cube root of 2. And that implies the cube root of 2, e to the 2 pi I over 3 cube root of 2, e to the 4 pi I over 3 cube root of 2, the other cube roots of unity, are conjugates. So somehow all of the roots are algebraically the same, and we'll see later that this idea of conjugates is helpful for figuring out where roots go under certain automorphisms. Something we looked at a little bit in chapter 1. Let me notice one thing though. You could say, well, what about the polynomial? Let's even put a cautionary sign. If we looked at the polynomial t squared plus 1 times t squared minus 2, the roots are plus or minus I plus or minus root 2. And you might be tempted to say that they're conjugates, but this guy here is not irreducible. It is evidently not, well, it's reducible, I should say. It's evidently reducible because I gave it to you factored, right? And somehow the fact that it's factored is saying that the roots here, the I roots and the root 2 roots, don't really interact. Well, of course you can multiply them, but you can't send one to the other, is what I mean by that. They don't have anything in common. One's the square root of 2, one's the square root of I. So be careful. You really need your polynomial to be irreducible for this idea of conjugates to really have any meaning. Here, all of the roots of this are plus or minus I plus or minus root 2. It's kind of irrelevant. We don't really get anything useful info about how to move the roots around. So these are not all conjugates. Of course, plus or minus I are conjugates on their own, plus or minus root 2 are conjugates on their own, but together they're not all conjugates of each other.